organic molecules, were attached to a metal. One was gringard reagent. Another one was a copper reagent. Another one was a lithium reagent, and that was it. Today there are thousands of organometallic compounds. Organo means an organic compound attached to a metal. When I went to graduate school, I took organometallic chemistry as a graduate class. There was no textbook because nobody had written one yet. There were 10 compounds we looked at. Today there's thousands of them. Today we take things like thallium, element 81, and there's hundreds of thallium organic compounds because those are insecticides and other things like that. So organometallic compounds have become a huge, huge deal in medicine and in chemistry. So the whole thing about organometallic chemistry is we have carbon. Carbon is nonpolar. It's in the middle of the periodic table. Doesn't gain, doesn't lose. Can't form ions in reality. We play around and say they're forming a semi-ion, but not really. So, how do we bond carbon to a metal? Well, it used to be very hard. Now it's trivial, and we can do this. And we're doing organometallic compounds. So, the way the reactions are going to work is, first of all, I want to take carbon and I want to attach it to a metal. Well, carbon is nonpolar. Metals are all positive. So how do I attach this carbon to the metal? And that's what I'm trying to do. It turns out what's going to happen is the carbon is going to become electronegative and the metal is going to become electropositive. And this is good because this is how we make carbon negative. In the long run, in organic chemistry, what do I want to do? Organic chemistry, I want to take one carbon and another carbon and I want to make them into a carbon-carbon bond. A carbon-carbon bond. The problem is, carbon is pretty neutral. It does form cations if we attach electronegative elements like oxygen and nitrogen and the halogens. We can make it fairly positive, and I can make things fairly positive by attaching some other substance like a chlorine or a halogen or something like that. I can make that carbon fairly positive. But in order to make a positive react with something else to make a new bond, this has to be negative. I want that to be negative. How do I make something in the middle of the periodic table negative? The only way is attach something way over on the left side of the periodic table, metal. So we want to attach carbon to a metal. In the old days we could do it. Now we have lots of ways to do it. So we're making these organometallic compounds. The reaction to do this, to make that, the reaction to make this is called a reaction called oxidative addition. Oxidative addition. In oxidative addition, a reagent adds to a metal. Causing a coordination, or the coordination. So, what we're going to have is something called a metal with L's, and these are called ligands. If you remember complex inorganic chemistry from Chem 1B, right? Complex compounds. So, a metal with ligands. No big deal. So this metal happens to have 4 attachments. And this shape is, of course, specific shape. What's it called? 2 main shapes of this type. This is square planar. And the other one would be and this type of complex is, what's the shape? Tetrahedral. This is tetrahedral. So we have a metal, and it's got four things around it. And that metal has a certain oxidation state. What does the term oxidation state mean? What does the term oxidation state mean? Is it the charge? Technical, chemical terms. Oxidation state versus charge.
We give oxygen to give out oxygen.
Oxidation state implies you've reacted with oxygen, so therefore you've changed your number of electrons. Oxidation state is the charge that that substance, the atom, appears to have in the compound. Oxidation state is the charge the element appears to have in the compound. It doesn't mean it's the real charge. It's the charge it appears to have in the compound. Oxidation state. Okay? So, these are not ionic compounds where all the ions are separated. It's not lithium chloride, where lithium is off by itself and chloride's off by itself. That's oxidation. That is the charge. Lithium is always positive 1 because it's off by itself and it's never in solution in water. It's off +1 and it's floating around. But once I bond it to something, the lithium appears to have a positive 1 charge if it was by itself, but it is not +1. And what we're going to look at is we're going to actually look at something like CH3 lithium. Now, this is a real compound. We're going to deal with that compound. We're going to actually have T-butyl lithium in the lab later on in the semester. Now, this compound is a compound. It is not ionic. It is partially ionic because of the ionic nature of the metal, but it is not ionic. It is 40% covalent, 60% ionic. It has ionic and covalent character. So, in this case, lithium has an oxidation state of +1. If it was by itself in water, it would have a charge of +1 because it's just the +1 ion. But its oxidation state in this compound is +1, and the carbon's oxidation state is -1. So the difference between charge and oxidation state. So here we have a metal, and it has a certain oxidation state. Now, what happens is we're going to add some substance AB, where A is positive and B is negative. And it just so happens A and B, acid and base, turns out in English works pretty good, but so it's just some ionic substance that has a positive and a negative piece attached to them. They do not have to be ionic compounds. They can be things like an organometallic compound or whatever. It's a compound that has two parts to it. What happens is this metal is going to now grab this. There are 2 electrons right there being used to hold those two things together because they're bonded. What's going to happen is those electrons are going to be used to help bond that to this metal. And what we're going to do is we're now going to end up the metal in the top, and we have now added to this. So A and B have now been added across the metal. We have now caused the coordination number of the metal to increase by 2. The coordination number of the metal in the first compound was what? Was 4. Coordination number just tells you how many ligands are attached. So the coordination number here is 4. The coordination number here is 6. This is all vocabulary that we're going to be using in the next semester. We're going to talk organometallic chemistry all the way to the end of this semester. So, I could use square planar or tetrahedral. metals with their ligands, and they're going to add some A and B, and it makes a coordination increase. Now, what's going to happen is the rest of the reaction is going to continue, and now one of these is going to go off with the ligands, and you're going to leave the other one attached to the metal. So, what we're going to form now is back to square planar. Here's the metal. Three of the ligands are still there, but the fourth ligand has gone away, and I now have B attached here, and I also have Al. And this is reductive elimination. What do I want? This is what I want, because there's my new metal B bond. The metal and the B bonded together. Now, it doesn't have to be just a metal complex like this. The Grignard reaction, what we're going to do is we're going to start with elemental magnesium. Elemental magnesium. And we're going to add some organic molecule. Now, I know it's elemental magnesium because we put a little zero up there, meaning it has no charge, so it's the element. Actually, solid magnesium. We're going to use solid magnesium in this reaction. What's going to happen is we're going to end up with what's known as a Grignard reagent. Auguste Grignard was a French chemist who won the Nobel Prize in 1913 for this reaction. It's still very commonly used all over the world as a way to make organometallic compounds, first of all. Now, another type of way that we explain this is we call this a reverse polarization reaction. Reverse polarization. Because what has happened? What's happened in this reaction? What we can see has happened is we start over here with an alkyl halide. This is organic, and there's a halogen. So we know there's a dipole there. Because of the electronegativity and the polarizability of the halogens, alkyl halides are polarized. The carbon is electropositive and the halogen is electronegative. But when we do the reaction, now look what has happened. Now the carbon is a negative and the carbon is a negative, the halogens are negative, and it's the magnesium that is now the positive. In fact, what is the magnesium now? 2 plus charge. So, what's happened? Magnesium has started out with 2 electrons. Right? Magnesium, periodic table, it's got 2 electrons on the outside energy level, and we're going to use those 2 electrons and these 2 electrons. So those 2 and these 2 are the 4 electrons here. Reverse polarization means that we've now taken a positive carbon and turned it into a negative carbon. Reverse polarization. The first person that actually wrote up the entire theory about all of this was Dieter Seebach, a German chemist, Swiss German, and he called this Umpolung. Umpolung in German means backwards. And so that's in pulling. So when I took the class, you had to learn the words in pulling and a few other things. But anyway, today we just call it reverse polarization type process. We're taking a carbon that's normally positive, turning it into negative. Why? So we can do this. We need a negative carbon to add to the positive carbon to make the carbon-carbon bond. So that's the beginning. And that's the end. I will see you on Thursday